All right. Our ultimate goal eventually, after about 4 or 3 videos, will be to get to Stokes' theorem and the divergence theorem. However, though we need to cover those topics are prerequisites to get into those two theorems. We're going to use the curl and divergence theorem as part of those theorems. And those theorems also need, or use rather, surface integrals. In order to get to surface integrals, we need to see parameterizations of surfaces. So this first topic is a little independent of those two. We need all three. So I guess we could do those two first, and then this one, or this one, and then those two. Either way, we need to cover all three. And those two are together. We need this one to get to surface integrals, but we don't necessarily need the curl or the divergence, I believe. Um, so we're gonna start in this video with curl and divergence. First, let's define an operator, which happens to be a vector, and we're gonna think of it as the derivative with respect to x, the partial with respect to y, partial with respect to z. And this is an operator vector. So it is going to do something to components of another vector. So again, this is an operator vector. Okay, it operates on other vectors. So the curl of f, and we're going to assume f is a, well, let me define this first. Will be this operator crossed with f itself. The divergence of f is going to be the operator dotted with the vector field itself. Okay. So to show how this works, we're going to assume that f of x, y, z will be p, q, r. And those are functions of x, y, z themselves. So this is a function of x, y, z, a function of x, y, z, a function of x, y, z. So all three are potentially functions of x, y, z. They could be very simple, like just x or just y or something like that. In fact, in the examples we're going to do in this video, those are going to be very, very simple. So the curl of f, we can think of it, I'm going to write this in a vertical fashion. It's easier for me to visualize. So partial with respect to x, partial with respect to y operator, partial with respect to z as an operator, and together they make an operator vector, crossed, because that is a definition. Those two are definitions, with p, q, r. All right, and remember how we do this. So the answer will be r sub y. So operate on r. Operate, by that we mean find the partial derivative of r with respect to y, minus partial derivative of q with respect to z, q sub z, comma, and then we do partial of r with respect to x, but that's going to be opposite. So r sub x plus p sub z, comma, and finally we're going to have q sub x minus p sub y, And by the way, that last term should be a little familiar to you. That is exactly what is used in Stokes' theorem. No, I'm sorry, in Green's theorem, which we saw in a previous video. This particular component was the partial of q with respect to x minus the partial of p with respect to y. So we're going to take note of that. there's a couple things I want to point out about the curl. When you have components P, Q, and R, we never have across this expression derivative of P with respect to X. If you pay close attention, there's no P sub X. There is no Q sub Y. Nope. And there is no R sub Z. There is no derivative of R with respect to Z. So no derivative of P with respect to X, no derivative of Q with respect to Y, no derivative of R with respect to Z shows up anywhere in the curl. On the divergence, on the other hand, I'm going to put pages on this. The divergence, on the other hand, um, we do have exactly the opposite situation. So in this case, we have the gradient operator. So that is going to be partial with respect to X, partial with respect to Y, partial with respect to Z, applied to P, Q, R correspondingly, and then we add them together. So we have P sub X plus Q sub Y plus R sub Z. Yep. So this is exactly the opposite. In this expression, even though we are doing a lot of, P sub Z, P sub Y, but there's no P sub X, nowhere in here. The P shows up twice, once with Y, once with Z. The Q shows up twice in this expression, once with X and once with Z, but not with Y. Here, the Q shows up with Y, but not with X or Z. And P shows up with X, but not not Y or Z, and R shows up with Z, but not with X and Y. The other thing to notice is that this is going to be a vector. The curl, I'm going to put that here, is a vector, while the divergence is a scalar. Yep, vector versus a scalar. And it is important to remember that. From the definition, there are a couple things we can immediately notice, and those are going to be theorems. There's two theorems. On one hand, we're going to have that the curl of the gradient of function is going to be 0, while the divergence of the curl of a vector field is also going to be 0. Now, even though I'm writing 0, those are different zeros. The 0 in those two equations, they're different zeros. Remember, the curl will always be a vector, while the divergence is a scalar. So oftentimes I will not put an arrow, although I will put probably 0, 0, 0. But if I put 0 on a curl, that means the vector 0, 0, 0. And the divergence is a scalar. Very, very important difference. Okay, let me give you a quick informal proof of this. So the curl of the gradient of a function, let's see, is gonna be obtained by finding partial with respect to X, partial with respect to Y, partial with respect to Z, crossed, multiplied with, now remember, the gradient of F is F sub X, F sub Y, F sub Z. And those are three-dimensional vectors. So when we cross, we get F sub ZY. Let's write it down. F of ZY minus F sub YZ. All right. I forget the name of the theorem. Curious, it's not curious. Anyway, there's a theorem. I should check it out. It just slipped my mind right now. Those the derivative with respect to z and y in that order versus the derivative with respect to y and z in the opposite order are going to be equal to each other. And so we're going to end up with 0. Those two quantities are going to end up being equal to each other. So when we subtract them, we end up with 0. So here we have yz as derivatives and yz as derivatives in different order, because here we have this z already performed, and then we're going to apply y after. The same thing is going to happen to the other components when we do the cross product. Here we have xz, xz in different order, but they end up being the same. And then xy and xy. So we're going to end up with 0 and 0. This is, again, very informal. This part, of course, will be 0. And likewise, there's going to be 0 across. Yeah. So that's why the curl of the divergence of a function is going to be the 0 vector. The divergence of a curl of a function, well, we could explain why. Okay, so the divergence of the curl. I can explain that visually here. So the divergence means we're going to do this component and then apply the partial with respect to x. Take this component, apply the derivative with respect to y. This component, apply the derivative with respect to z. All right, so apply the derivative of x, apply the derivative of y to that, apply the derivative of z, but then we're going to add those three products or those three outputs that we obtain. Okay, so here we're going to end up with r sub xy, and here we're going to end up with r sub xy as well, because here we're going to apply the x, and here we're going to apply the y. One positive, one negative, they simplify down to 0. And the same thing is going to happen across. So again, apply the x derivative. We're going to have q zx. Apply the derivative with respect to z, and we're going to have q xz versus zx. And those two are going to simplify down to 0, because the derivative with respect to x and z is the same thing as the derivative with respect to z and x. Man, again, I'm forgetting the name of this very, very important theorem. It is embarrassing. I must be very distracted today. Yes, and then those are going to add up to 0. Let me pause for a moment while I check the spelling of that theorem. Okay, I'm back. Yep, it's Clairaut's theorem. Boy, I'm just going to put it here. It is the one, it is an important theorem, so I should not neglect it. So again, that theorem says that if you take derivatives under certain conditions, and a lot of the problems we're going to work on have those conditions. If we take derivatives with respect to zy versus yz, they are going to end up being the same, so that's why we end up with 0. Clairaut's theorem allows us to do that. Back to this other fact. Oh, I was explaining that here. We're going to end up with zeros because all of the terms, such as x, q, x, z is going to show up here with opposite sign when we add them together. And so they're going to cancel off, and we're going to end up with zeros. So that is just a very informal and visual way to show that those two are correct. Now, we can extract some information out of this theorem. This tells us that if we have a vector field that comes from the gradient of another function, the curl is going to be equal to 0. In particular, if you take the curl of a function and you don't obtain 0, that means that that function did not come from a gradient. So that function is not, that vector field is not conservative. See, a question we ask ourselves is whether a function is conservative or not. If it is conservative, then, as we have seen in previous videos, we can have independence of paths. So it is important to know whether a function is conservative or not, a vector field rather, is conservative or not. Now, in a previous video, the way we found whether something is conservative or not is by finding the derivative with respect to y. So we get p sub y, and then derivative here with respect to x. So we get q sub x. And if they happen to be equal, then that means there is a source function that after doing the gradient, we get this vector field. By the way, we can rewrite this as qx minus py, which shows up, by the way, on Green's theorem. This term shows up in Green's theorem, and it shows up here as the third component of the curl, qx minus py, equal to 0. If we get equal to 0, then there is such an f. Okay, if this component is equal to 0. Well, this is useful in 2 dimensions. What if we have 3 dimensions? What if we have P, Q, R in 3 dimensions? Okay, so what are we gonna compare? P sub Z, P sub Y? What's the deal? Are we gonna compare with Q? What Q are we gonna compare? So it's not, we have 3 components and we're not gonna prefer those 2 over the other one. And it's not easy to figure out if there is an F that after doing the gradient will give us those components. It's not easy. It's not, definitely not easy to figure that out. But we can find the curl of PQR, which would be, typically we call that F. Okay, so PQR. And if we get 0, then yes, we will have a function whose gradient is this vector field, just like we did back here. Yep. So there's a value to this theorem. We can, and again, the theorem says that this is equal to 0. So if we don't have a 0, we don't have a function whose gradient is the given vector field. But if we add more conditions of continuity and so forth, nice conditions, then the theorem goes both ways. So this is assuming that things are reasonably nice, you know, there's not a lot of discontinuities and such, then this tells us whether we have a conservative field or not, this test. If we get 0, conservative. If we get something that is not 0, not conservative. All right. I want to emphasize again that this part shows up in Green's theorem. So I just want to rewrite Green's theorem differently. Green's theorem. This allows us to write the Green's theorem a little differently. So originally we have this, the double integral of q sub x minus p sub y with respect to the area is the line integral all the way around d. So it's a closed one of f with respect to the path. There you go. So that is originally Green's theorem. Now this is one of the components of the curl. The curl has that particular expression as one of the components. If you want to pick up that component from the curl, we can do that component from the curl by simply doing the dot product with 0, 0, 1. All right, so what we are saying is that the double integral over d of the curl of f dotted with 0, 0, 1 with respect to the area will be equal to the line integral, the closed line integral of f. Okay, but there is one problem. This is in 3 dimensions, and the original problem did not have 3 dimensions. F in the original Green's theorem had uh, only 2 components, PQ, no Z component here. We do have a general line integral with 3 components, but for purposes of Green's theorem, which is in the XY plane, we only have 2 components. So if F is made up by PQ, then here we have to change F. We have to have a different F, PQ 0. Yeah, that dr. In practice, and then the R has to be affected. It has to be a 3-dimensional path with 0 on the 3rd component. I guess it doesn't make any difference. When you do the dot product, it won't make any difference. But I feel better if things match as far as, yeah, being 3-dimensional versus 2-dimensional. So can we rewrite Green's theorem using the curl? And the answer is yes. We are picking up the 3rd component of the curl, and then we're making sure that the dimension is correct. A 2-dimensional vector is not the same as a 3-dimensional vector, even if you put a 0 on it. Those are different objects. So we have to make sure we're changing the function. We're embedding the function into 3 dimensions. That's called officially embedding, and we will be doing the same thing with the R. In practice, we would not want to do this, though. Why not? Because finding the curl is more work than finding just one of the components of the curl. What is the point of finding the curl 3 components if we're going to drop 2 of them anyway? So in practice, this is not very valuable. Yeah, right now. Yeah. Yep. Yep. But it's neat to see how the curl can be seen as, or we can write Green's theorem using the curl. Okay, let's start some examples of curl and divergence. So example 1, let's define XYZ as 0, 0, 1. Okay, so we have a field with a bunch of vectors going up. So this is a flow, if you want to think that way, of air going up. Pretend there's a huge fan and way down here, and all the air is going up exactly in the same way. So I don't know if a fan will do that. I don't know enough about flow mechanics, but pretend there is just a constant flow of air going up. So if a particle is floating here, it will just be picked up by the wind and move uniformly up with a constant speed. So the curl of F, now let's think about this. The curl uses partial derivatives all over. Partial. So all of those are partial derivatives. So the partial derivative of 0, of course, is 0, 0. The partial derivative of 1 is 0. The curl is going to be 0, 0, 0. There is no curl. Well, there is a curl, which is just 0, 0, 0. And even if we add or subtract, as we are doing here, derivatives, all of them are going to be 0. So we're going to be adding and subtracting a bunch of zeros. So yeah. So the curl of this is 0. Again, we have a continuous, nice, smooth, in one direction a flow, and the curl is going to be 0. The divergence of F, which is partial of that with respect to X, partial of that with respect to Y, partial of that with respect to Z, well, it's just going to be 0, 0, 0 again. So the answer is going to be 0. So even though everything is moving up at a constant speed and in the same direction, we're going to end up zero with zero curl and zero divergence. In fact, uh, let's write this as a note. Note, same is true for f of x, y, z. And you can just put any three numbers, 2, 3, 5. And the same logic, the same thinking will tell us that the curl is going to be 0, 0, 0, and the divergence is going to be 0. So if we have a continuous flow in all of the vectors in one direction, it doesn't matter which direction, you're going to end up with a curl of 0 and a divergence of 0. Yep. Let's look at a second example. So example 2, sometimes to understand a concept, it is a good idea to apply the concept to many simple examples to see what happens. So x, y, z. What about 0, 0, z instead of 1, z? So what happens here is that the points that are close to the xy plane are going to have a small flow upward, and the farther we are from the xy plane, the flow is going to go vertical up with more flow. There's more to it. Because we're farther away from the xy plane, the z is going to be larger, and consequently, those vectors are going to be larger. So the farther you are, the longer the vectors. Furthermore, if you go below the xy plane, the vectors are going to go on the opposite direction. They're going to go down. And the farther away they are, the longer they will be. Okay. So what is the curl? The curl of f, all right, remember the curl is this formula. The only thing that is not 0 is going to be PQR, R. So, but R is operated just by the derivative with respect to y. There's no y here, so we're going to end up with 0. And with respect to x, and there's no x here, so we're going to end up with 0. So the curl is still 0, 0, 0. Yep. And the divergence is going to be the derivative of that with respect to x, y, and z. The only one that does have something is z, and we're going to end up with 1. So that is interesting. The divergence is 1, perhaps because the vectors are getting longer as opposed to this one where the vectors are not getting longer. The divergence is 0. In both cases, the curl is 0. The curl gives us the direction of the axis of rotation. By the way, I'm going to squeeze a quick picture here that has, so if there is some kind of rotation in the flow, yep, the curl gives us the vector, the direction of this perpendicular to the center of the rotation. So if we have some kind of rotation this way, that's what the curl gives us. All right. Example 3. Let's say we have 0, 0, x. F, x, y, z equals 0, 0, x. All right. So all of those outputs are going to go up or down because we got 0, 0. And again, that's going to tell us that we're going to go up or down depending on the x value. So when x is positive, okay, we're going to have vectors going up. The farther away we're from the origin in the x direction, in the positive x direction, the longer they will be. So these are going to be even longer. And once we get to this level, they're going to be the same length. So they're short here, and then they increase as we go this way. Across, going in the y direction, they're not going to increase because x is the only thing that affects the outputs. Even down here, we'll have the same situation. And then they get shorter and shorter yet. But if we go past the YZ plane, behind the YZ plane, then the vectors are going to go down because the x's are going to be negative. So the farther away we are, the longer they are. So on this side of the YZ plane, we're going to go up. On the other side of the YZ plane, we're going to go down, up and down, up and down. So we could have, in fact, some kind of rotation. Yeah, so if a particle is here, it's going to go up, 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 up. But if the particles, if there's an additional force that pushes it in that direction towards the XZ plane, rather YZ plane, and it catches the other side, then it is going to start going down. All right, what is the curl? C-U-R-L, curl of F. All right, I'm going to imagine I have the operator up here, so I don't have to actually write down the two. So y, that's going to be 0, 0. So the first component is 0. The second component is going to be 1, and actually -1 and 0. And the third component is going to be 0. So just pretend you have, if you need to write it down, you could just write down your operators up here and then do the cross product of vectors. We get -1, which is a vector. I'm going to draw a new picture. X, Y, Z. So that's a vector going in that direction, which makes sense because if we think of this as having a rotation up and down, the y-axis, it would be sort of the center of rotation. Actually, anything on the that is parallel to the y-axis, above or below the y-axis, could be thought of as a center of rotation. And the vector goes that way. That would be 0, -1, 0. The divergence, on the other hand, of this F is 0. 0, 0. The derivative of this with respect to Z is 0. So that is interesting. We have a divergence of 0, but we have a curl that is not 0. Okay, example 4. Let me show you how I came up with example 4. Okay, if you have a point, just a generic point on the XY plane. Let me draw the line that joins the origin to that. So let's label this as AB. And I want to find a vector that is perpendicular to this line that joins the origin to this point. Perpendicular, going in the counterclockwise direction. So positive direction if there's a rotation. So this way. What are the coordinates of this vector? Well, if we want it to be perpendicular of the same length, either it has to be -b comma a or b comma -a. But because we want it to go in the counterclockwise direction, this vector has coordinates -b a. And the same thing will happen anywhere. If you have a vector here and you want the perpendicular going in the counterclockwise direction, you do. So again, if this was A, B, this should be tilted a little more. It almost looks horizontal because this is, say this is off vertical, so this should be off the horizontal by the same amount, by the same angle. So pretend this is lower. Anyhow, this is still gonna be opposite of B. Yeah, because B would be in this case negative, so opposite means to the right. Yep, And opposite of B. So if this was A, B to start with, this vector. So B would be going down. Okay, we want it to go forward. Oh yeah, but A does not change. A is still negative. Good. So we're good. So this rule of negative BA always provides us, no matter where you are, if you're here, with a vector that is perpendicular going in the counterclockwise direction, etc. Okay. So the question is, rather, there's no question yet. Let's build a vector field x, y, z with that principle. Um, Opposite of y, x, 0. So what does that do? If you're here, you're going to get a vector that is perpendicular. If you're here, you're going to get a vector that is perpendicular. Whoops, that way, and so forth. So vectors that are perpendicular going counterclockwise. So now we're going to go this way. And here we're going to go this way. Yep. So we're going around. And if you're diagonal, oh, this symbol is bad. But there, now we're changing it. We're going in this direction. So it's unfortunate that this looks like something that is not very nice. But I just want to show the vectors. So the vectors at any given point go around, and the closer the point to the z-axis, the smaller the circle that goes around. Yeah. And the farther away, the larger the circle that goes around. And the axis of rotation will be z. So without doing work, I expect the axis of rotation, or rather the curl, to be this axis of rotation, or be parallel to the axis of rotation, which would be z. Well, let's see if that is true. So the curl of f is, okay, so I'm imagining here I have my operator. So y on this is going to be 0 minus z. Nope, that's going to be 0. And then x is 0. Operator or derivative with respect to z of y is also going to give us 0. And finally, we get 1 plus 1. So we get 2. And so sure enough, the curl is parallel to the positive z-axis. Yep, that is really neat. The divergence is going to be, of f is going to be 0, because derivative with respect to x, derivative with respect to y, derivative with respect to z, all of them are going to be 0. Add them together, we get 0. So no divergence, but we do see the curl, because we do see some swirling around. Something important to note that we had f equals negative y x 5, we still would have curl of f equal to 0, 0, 2. Is that so? Let's see. If this was a 5, we would do, yeah, the derivative of 5 is 0. So it just the same as the derivative of 0 is 0, regardless of what variable we are using. So sure enough, whether this was a 5, a 7, a 3, or a 2, whatever, or a negative 1, as long as we have a constant, we would end up with the same curl, which is very interesting. So if these vectors were going up at the same time as going around, but up, so a particle would be going up while it was going around, as in a helix, we would end up with the same curl and the same divergence. So what is important about this is how things are swirling around the z-axis. And here we have a curl that is parallel to the positive z-axis. I'm just looking to see, yep, that is my last example. So again, we are here right now. We can check the curl. The examples we did are very, very simple, but the ones you would find in typical classic books, calculus books, are a little more involved, but it is the same idea, the same concept. And what we're doing is essentially just introducing the concept, because we're not gonna do a lot of that until we get to Stokes and divergence theorem. So right now we are doing some concept. The next video will be about parameterization of surfaces, and then the next one about surface integrals, because we need parameterization of surfaces in order to do surface integrals. And we need surface integrals in order to start working on Stokes' theorem. So right now we're here, and we're gonna move on to the other two in future videos. All right, we'll stop here.